All right, so today we are going to continue on with our trace evidence unit. Again, this comprises multiple chapters out of the text, um, but instead of doing each as its own standalone chapter, I just kind of combined everything all into one because at the end of the day, really, it's all different forms of trace evidence that could show up at crime scenes or at different events that might need to be processed. So again, we've talked about hair, we've talked about pollen and spores, we've talked about soil, we've talked about fibers and textiles. So we've covered a wide range of topics thus far. And so today we're going to discuss glass. Um, and glass is a fairly common type of material that could potentially show up at crime scenes or at different events, whether you're talking like automobile accidents, hit and runs, hit and skips, any of those types of things. It's not uncommon to find those, even like car burglaries. If you have someone that's breaking into cars, it's possible that they end up with pieces of glass that are in articles of their clothing. And so those would need to be analyzed to see whether or not potentially that individual was present at that particular location, maybe when a crime was being committed or when something was being done. So again, it is a very common piece of evidence, and so it makes sense that we at least discuss it, at least on some level. All right, so let's get started here. In terms of glass, like I said, it is something that is very, very common that's going to show up in um, as a piece of trace evidence. Like I said, auto accidents, burglaries, and again, you can find different uh, other pieces of evidence that could be attached to the glass as well, whether someone's been cut or whether maybe they were crawling through an open window or a broken window and snagged an article of clothing. Again, any number of things could potentially take place. So it's important to understand the importance of glass as an item of trace evidence. But when you look at glass, really glass is a naturally occurring material. Whether you're talking volcanic activity, lightning strikes, any of those types of things um, can form glass naturally. Humans actually figured out glass making kind of by accident. You had individuals that were cooking on different rocks that had different chemical compounds in them, and as a result, as they were heated up with some sand, the sand and the different nitrates that were part of those rocks ended up melting together to form a type of glass, and so obviously people kind of connected the dots and are like, oh, hey, this is kind of handy. Um, so that was an accidental discovery, but once that occurred, again, we're talking about during Roman times, uh, but glass beads showed up in about 2500 BC, and that just simply continued on. Glass blowing began in the first century BC, and then obviously from that point on, it just began to grow. In the late 1200s, it was a big kind of secretive type of profession in Italy, and then by the 14th century, much of Europe was experiencing the ability to manufacture glass, and obviously the Industrial Revolution just saw that ramp up even more. So while it started out as a naturally occurring material, as humans, we figured out how to manipulate that process for our benefit. And obviously, I guess you could say the rest really is kind of history in terms of where it's at today. Today, we can do all kinds of things with glass, which is really a good thing for us. So, glass is, by definition, a hard amorphous solid, and what that simply means, the amorphous portion means that um, the the atoms that make up that particular material are not locked into place, so to speak. You don't find the crystal structure. So, like if you were to break salt, it's going to have a very specific pattern, right? That's why salt grains have the pattern that they do. And that's not the only thing. I mean, there's lots of examples of other minerals that are going to have a very specific pattern as a result of the way the atoms that make up that material have bonded together. Well, with glass, you don't see that same type of interaction, and so glass is not a regular material in terms of being able to predict what it's going to look like when it fractures. In addition to that, the amorphous part, again, those atoms can move even after the glass has been formed. So really, really, really old glass, like in old houses or churches or whatever, will become thinner at the top and thicker at the bottom as those atoms are able to gradually and very slowly move over time, which I find kind of interesting to think about something that we consider to be so hard. Um, to still be able to have some properties that allow it to be able to move quite a little bit. But the materials that are going to go together, the silicon oxide that you're going to find in sand, we're going to add to that calcium oxide and then sodium oxide, and that forms our soda lime glass. Of all the types of glasses, soda lime glass is going to be one of the most common types that you're going to find. Um, because of its characteristics, it can be polished and decorated, and you can obviously make it into a lot of different shapes while it's hot. And so again, it's going to be one of the most common ones that will be used for like glass blowing and things like that. Okay, but because of that, it's relatively inexpensive, and so because of that, it still maintains its strength. And so again, because it's a very common um, formula, if you will, or a recipe. I don't know how you want to describe it, but the way that it's made is very common, and so it makes it relatively easy to recycle as well, which ends up being a good thing, especially in this day and age. Now, depending upon the materials that are added to the glass, you can change its composition pretty significantly. And if you do that, you now are going to impart new characteristics and abilities to that glass. So, for example, if you were to add lead oxide to the glass and create leaded glass, that's what's going to be used for fine glassware and decorative types of art glass. Um, and so again, you can add other materials to it to make Pyrex or Kymex, the different materials that are going to be used in lab settings. You're going to add different materials to make headlights in automobiles. By adding different metals to it, you can end up producing colorations, various colors that again can be used for decorative purposes or even for specific uses within maybe an industrial setting or something like that. So again, there's lots of things that we can do to this to make it um, more user friendly, I guess, at the end. So again, changing materials is going to change the characteristics that it's going to have. So again, you're going to end up with whatever it is that we want um, as an end product. Okay. However, when we look at glass, there are several um, properties that we're going to look at, or at least a couple properties that we're going to look at that are going to be fairly consistent. Okay. The first one is going to be that of density. And density is just a measure of the mass divided by the volume. So this picture does a nice job of showing how to determine the density of a piece of glass. If you have a small enough piece that would fit into a graduated cylinder, you simply put a known volume of water into that graduated cylinder. You then deposit that piece of glass, and you see how much does that level of water raise with that piece of glass in there. And so that's going to tell you the volume of it. You put the piece of glass on a digital balance, and you're going to get its mass. So you take your mass divided by volume, and ta-da, you're going to have its density. Now, where that becomes important is if you've got maybe a couple different pieces of glass that you want to compare. And so you can take those pieces of glass and compare their density to see whether or not they're from the same source or whether they're from different sources. So let's say maybe you have piece of glass that you believe came from the headlamp or headlight of an automobile, and you've got a car that has a broken headlamp. You could take a piece of glass from the headlamp. You could take your suspected piece of glass that you found at the scene. You could compare the density of those two to determine whether or not they're from the same source, whether that piece that you have came from that headlamp or not. Again, it's not a foolproof method, uh, but it is useful in terms of at least initially determining whether or not those two pieces are similar. Another property that's going to be very useful is what's known as the refractive index. It's represented by the N, the letter N in this particular context, and simply it's a measure of how light bends as it moves from one medium into another, right? So whether it's air into glass, as it describes here, or whether we're talking about air into water, or any number of other mediums, right? That just as that light moves through that medium, how does it behave? And what we know is that as light travels through the air, there are very few things that it's going to interact with that are going to slow it down. However, because of the particles in glass or particles in water, when that occurs, the light is going to slow down significantly. Well, as it does so, that light then is going to be caused to bend in a particular direction. Okay. Now, you'll notice in this picture there is what's referred to as the normal line. This normal line is an imaginary line that exists that is perpendicular to the surface of the medium that the light is traveling into. Okay. So, and you'll notice it extends from the air. Imagine it through the surface of the glass. So this is the surface of the glass. Again, it's not to scale or anything. We imagine that the other side of the glass is over here. All right, it doesn't matter. But what happens is as that light moves through that glass, because it slows down, it changes the angle. So normally, if it were to go uninterrupted, it would continue in this type of direction, right? It would be just a continuation of this line. But because of the way the light interacts and slows down, it causes the light to bend towards that normal line. So again, remember the normal line extends from the air through the medium, all right, at a 90-degree angle, and so it's going to bend towards that normal line. Okay, so it's the light is always going to move um, towards the normal line if it's into a denser material. If it's into a less dense material, so imagine, let's take our arrows and flip them. So this arrow now would point towards the sun. This arrow would point towards the sun. It would move away from that normal line. Okay. So again, that can be used to calculate it. So light's going to bend towards the line perpendicular to the surface where the two surfaces meet, right? That's the normal line when moving from a less dense to a more dense medium. So from air, which is less dense, notice its refractive index is 1. Notice the refractive index of glass is 1.52, so it's slightly higher. And so that causes the light to move towards the normal line. Okay. So there is a mathematical equation that describes the behavior of light as it moves from one medium into another. And it's simply the refractive index of medium 1 times the sine of angle 1, and that's going to be equivalent to the refractive index of material 2, or medium 2, sorry, and the sine of angle 2. So again, we could plug all of this in. We have our refractive index of air is 1. Our sine of angle 1, we don't know. We can calculate it, is going to equal our refractive index 1.52 times the sine of 25. And that then would allow us to figure out, well, what is the angle of angle 1? I don't have a calculator here with me right now. But again, if you were to put it in that particular fashion, that's how you would solve it. Relatively simple, I think. Okay. And so, again, this is just a description of what each of the different variables are going to represent. So that's another characteristic. So we have density, we have the refractive index, and then we also have another one that's going to kind of combine the refractive index and going to be what we're going to look at in terms of Beck lines. Okay, but you can take your unknown glass, you can submerge it in a liquid that has a known um, refractive index. right? So if we know the refractive index of a particular material and we submerge, and different materials have different refractive indices, but if you were to take and submerge that piece of glass um, in that liquid, if the refractive indices of the glass and the liquid are the same or nearly the same, you're going to not be able to really see that piece of glass. It's going to almost disappear as it's submerged in that solution. Okay. However, if the materials or the refractive indices of the glass and the liquids are not the same, you can end up with what are referred to as these Beck lines. Okay, and so the Beck lines, when exposed to light, right, those are going to be formed on the material that has the higher refractive index. Okay, so in this case, the glass has the higher refractive index because the lines, the white Beck lines, are formed inside the piece of glass. Right, this is our fragment of glass. Conversely, in this one, notice these white Beck lines, they're going to exist outside of the piece of glass. So that tells us that the liquid that they're submerged in is going to have a higher refractive index than the piece of glass. All right, and so you can see here in terms of what we're going to look at. Okay. All right. Again, you can look at thickness of glass. That's going to be a very general and very vague one, not one that's going to be super useful. Now, one of the things that ends up being useful is being able to determine the order of events that maybe have occurred. Maybe you've got someone that was found, or yeah, maybe was found at the scene of a burglary or at a break-in, and they claim, well, I didn't commit the break-in. It was already done. Maybe you find pieces of glass on their person or whatever, or maybe you have an event that's taken place. Maybe someone is unfortunately shot in a vehicle, and you need to want to be able to figure out the order of events. Maybe you have multiple individuals in the vehicle, and you need to figure out which of the individuals was shot first, and so on and so forth. Or maybe you have individuals that exchanged gunfire, one from inside the vehicle, one from outside. And you want to be able to determine the order of kind of which individual shot first, the person outside the vehicle, the person inside. And so you can look at the fracture patterns that end up being generated. But with this, obviously, glass, the beauty of glass is that it is very strong for the most part. It does have the ability to flex as it's put under tension. But like many things, if the tension is great enough, then you're going to end up with that glass that's going to fracture. And so we can look at those fracture patterns to determine kind of what took place. So let's say, for example, we've got maybe a BB that's passed through a window. Maybe you've got some young people that were out shooting windows out of an old building or out of cars. Unfortunately, uh, sometimes people make bad choices, and those are some of the bad choices that they'll sometimes make. But what you're going to end up with as that item, whether it's a BB, a bullet, a baseball, even, right, as it makes its way through that piece of glass, that's going to create a force, a tension force, right where that uh, object contacts the glass initially. Well, as it does so, it causes that glass to flex, not only where it hits, but also then around it as well. And you'll notice that where it hits, that fracture is going to occur on the opposite side of the force. So in the event of like a bullet or a BB, you're going to end up with some of this glass on the back side being broken out. So even if you could put it all back together, you would end up with a pocket or an opening or a hole on the backside of the glass. Um, so again, that can be useful. But from that, you're going to end up with radial fractures that are going to go out from that point of impact. Okay, they're going to radiate out from that point of impact, and they'll go out in many different directions. As you can see on here, you've got lots of radial fractures that occurred as a result of this object passing through the glass. Um, Subsequent to that, what you will then get are a series of concentric fractures, the fractures that then move around that particular object passing through uh, that window. Um, and they're going to form on the same side as the force of that object. Okay, so they form on the same side, whereas your radial fractures are going to occur um, on the backside. The radiating fractures form on the backside of that particular piece of glass. Okay, so concentric on the same side, radiating fractures are going to be on the backside. And again, you can figure out order of events because your initial breaks will stop any other break from occurring. All right. So let's say there was another item here, another hole in the glass, and it started to crack. They would run until they stopped stopped because this glass is already fractured, so it can't continue on. Right. So that would stop at that particular radiating fracture or the concentric fracture or whatever. Okay. And so that ends up being obviously very, very important. So you'll notice the force, all right, they're going to form as a result of these particular um, fractures. Notice that the right angle is on the backside away from the direction of the force. But notice that you also end up with pieces of glass that end up being displaced. Okay, so you're going to end up with that pocket or hole on that backside. In terms of handling the samples that you may find, much like we've talked about with the others, the documentation is going to be very important. You want to photograph everything from multiple angles. You want to make note of anything that you find embedded in the glass, whether it's hair, whether it's fibers, whether it's tissue, whether it's mud. In the event of maybe, let's say, like an automobile accident, maybe you have a filament that's been embedded in the glass because it was hot when the accident occurred. You want to make note of all of those things, and you want to get good pictures of them. You want to include them in your drawing, your crime scene drawing, to be able to document where those materials came from. That's going to be very, very important in terms of creating that applicable chain of custody. So yeah, note any material that you find, whatever, and then you're going to collect the samples that you're going to need. And again, you're going to collect multiple samples. It's not just one piece and we're good. You want to collect multiple samples. So maybe a sample from here, sample from here, sample from here, sample from here and here. And again, you're going to put them into their own individual containers. You're going to label them with who collected them, when they were collected, what the case number is, da 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 da. You get the idea. All of the different things that we've discussed already, you're going to label those as well. Once you have them, then you can take them back to the lab and you can perform the basic density, refractive indices, and Beck lines test on, right? And then you'll be able to determine whether or not those pieces of glass were from the same source, at least hopefully. Again, rarely would glass be the standalone piece of evidence that's going to be necessary in a um, court of law, uh, but it's just another piece to the puzzle, so to speak, that allows us to be able to kind of connect the dots and show, yes, these individuals were at that location when that particular event occurred. Okay. All right. Again, you want to make sure you collect sufficient samples, and there's that. Okay. So the next thing that we'll be talking about will be the casts and impressions, but we'll save that for next time. Again, if you have any questions, please feel free to reach out to me. Otherwise, I will talk to you soon.